Okay, let's get started. So just putting this up here so you can see the exam 3 review is available to you. I put the 325 one. I wasn't ready to put the 321. Sorry about that. That was really weird. I'm not sure what happened. Can you still hear me in TV land?
Yeah, I can still hear you.
Okay, there was just some weird technical glitch, I guess. So what I was saying is it's not intended to be the details. It's just to kind of hit some of the points and give a high level narrative discussion. So if you want the details, you look at the slide presentations as well as watch the videos, right? That's what we have, that additional material, but it will hopefully just give you some ways to optimize your studying and to kind of check what your learning is. If you roll through those and it makes perfect sense, you probably don't need to study all that much in that particular section. If it doesn't make a lot of sense, then you probably want to spend more time. Also with the questions, I didn't put them into any specific section because in AC circuits material builds on it. So it wouldn't make sense to say this problem only would be referenced in this particular section because it actually builds on 3 or 4 sections. In addition, right, we do a lot of 3-phase power calculations. When do you use 3? When do you use square root of 3? When do you use cosine theta? So you would have to include that material as well, right? So this material will build on it. And I will say we had a discussion last Friday about EET students and some of the FE stuff, and it sounds like we're messing up 3 versus square root of 3. So I said, hopefully not in this class, right? So hopefully it's all peachy keen. Not a threat. That's just, you better do it. Okay. No, but it's a pretty simple topic if you just keep track of it, right? So the reason why I'm stating that is because it's not a difficult or challenging topic to remember. You just need to think about, why do I use the square root of 3 versus 3? Okay. But that is available for you up there. And our test will be a week from Thursday. And it'll cover the induction motor material that we've covered. So we'll cover up to Thursday, and then next Tuesday we'll do a review session. So whatever questions you may have. All right. Okay. Any questions on anything before we get back into the presentations? Somebody raise their hand first. One of you two. We will, but we won't have a ton of material because normally the Tuesday after the class, we go after, we go over the final of the test. And then that Thursday will be a little bit of discussion, but probably more of a semester in review. So we won't have a lot of time to cover any new material.
And then for the homework on Thursday, you're gonna bump those to next week again. Is that kind of late? Thursday.
I had that kind of, what do you mean? That homework's been posted for.
Yeah, the last time we got that, like to the next week.
Well, again, so that I think the reason why I changed it is there was a request, but the homework will help you study for the test, right? That's the reason why it's due on that day. It's not to give you extra work. It's hopefully to help you. But if people don't want to do that day, that's up to you. I don't have a preference. Is it due this Thursday? I don't remember. I'd have to look. I can make it due Tuesday. And then you can ask questions about it. Okay, I can push that off. Yep, okay, anything else? Okay. Wait for my computer to connect up to speed. Here we go. All right, so let's look at a different case, and we're just going to mix up a little bit with frequency just to show that all the calculations and work is exactly the same. So we have a 2-pole 50 hertz induction machine. So 50 or 60 hertz, it doesn't matter. It's supplying 15 kilowatts to a load, and its speed of operation, not its synchronous speed, but its speed of operation is just under 3,000 RPM. And you know it's 2-pole because it says it, but you also know because it's just under 3,000 RPM or 2950, that this would normally be a 2-pole machine, because we want to operate our machines as close to synchronous speed as possible, so we don't have a lot of resistance in our rotor circuit. I mean, a lot of losses in our rotor circuit. So the first question is, what's the motor slip? How much is it slipping? What is the induced torque in the motor under these conditions? So based on that speed of operation and the output power, what is the torque in Newton meters? If you double the torque, so this is where we start getting new material. If you double the operating speed, sorry, if you double the torque, what is going to be the new operating speed? All right. So hopefully when you start to look at this problem, you start to think, well, I'm increasing the amount of torque. Remember my torque versus speed characteristics, the motor needs to slow down, right? Not speed up. It needs to slow down because it's rising up that curve. And then, just for giggles, we're going to see if we double the torque, will we double the amount of power that is delivered? We'll take a look at that. All right, so we know what synchronous speed is for a 2-pole 50 hertz machine. It's 3,000 RPM. Our synchronous speed minus our mechanical speed divided by the nominal speed or the synchronous speed is going to be 1.67%. So really low value of slip, which again is what we would hope for if we want efficient operation. There's no friction and windage losses, so we're going to assume that all our converted power is going to go to the load, okay? Remember, converted power is different than air gap power. Air gap is what goes from stator to the rotor. Converted power is the rotor power minus any rotor copper losses. So we just have to keep those in the back of my mind. If you get confused, just go ahead and look up that curve that shows when power is being dropped off. So no friction and windage, which means all the converted power is going to be delivered to load power, and our induced torque is going to be the same as our load torque. So with that being said, our output power or load power is the same as our converted power. And we're going to convert our mechanical speed, which is an RPM, to radians per second, because when we divide watts by radians per second, we get Newton meters. So 15 kilowatts divided by 2950 RPM converted to radians per second gives us 48.6 Newton meters. All right, so let's double it. Yes, sir.
Wouldn't that be conversion from like RPM to radians per second?
What's that?
I'm just thinking radians. I was thinking to be some over
You sure? You can always just do this, right? So you have 2 pi radians per 1 revolution. You can do the conversions that way, right? Whenever you get stuck, just write it out. That's just the way I do it. I can't remember what it is, so I just write it out. Okay, so when we are in their low slip region, remember our torque versus speed curve kind of looks like this. And we're assuming it's a real, it's a very linear straight line. And we don't have a lot of data about its operation. So what we're gonna do is if we double the torque, then our speed is gonna be reduced. And the level it's gonna be reduced is we're gonna double the slip. Okay, we have no way of knowing without having the actual curve. So here is the next best thing. So you're gonna double your slip to 3.33%. Our new motor speed is gonna be 2,900 RPM. Now, our output power, you've got a doubling of the torque, so you just multiply that by 2. And we don't double the speed, right? Or not double the speed. We double the slip, but that means that our speed is reduced by 50 RPM or double what the slip speed is. So we don't get 30 kilowatts, we get 29.5 because power is equal to torque times omega. The power is a function of not only the torque, but also the speed of rotation. So it's not a doubling. The only way it would actually double the output is if the speed was constant. So in the case of a synchronous machine, if we double the torque, then we would say we doubled the amount of power output. Whereas in an induction motor, it's not necessarily the case. All right, so really simple way to solve these problems is when you're close to your mechanical nominal speed, if you need to double the torque or halve the torque, just double or halve the slip and then do all your calculations. This is torque versus speed. So this is torque and this is usually RPM, but it could be in radians per second or whatever you want. Yep. All right, let's do another problem. And this one is going to look at a little bit of information, but we're going to tweak our data where we said if our rotor resistance is doubled, because we talked before about doubling the torque and how we change the speed. Now we're going to increase the rotor resistance by most likely injecting some resistance in there and seeing what our new starting torque is going to be and see if there's any discrepancies. And then you're going to calculate and plot your torque versus speed characteristic curves for both cases. Item number 4 says calculate and plot. What that tells me is I've got to do some calculations, lots of calculations. So this would be a perfect one to do with MATLAB, right? All right, so we have all that data. So we're going to use this part to calculate our synchronous speed. Well, really those two, right? That's going to calculate our synchronous speed. It's Y connected, which tells us what our voltage is going to be, not 460 volts per phase. It's 460 divided by the square root of 3. And our 25 horsepower is just a nominal output rating. That doesn't mean that the machine is putting out 25 horsepower. Here are all our impedances, R1, R2, X1, X2, XM. We're not giving any core losses. So we'll do that. So let's go ahead and draw our parameters. Oops, I'll put the actual numbers in there. So this is 0.332 over slip. And notice that my slip is not known at this point, right? So I have to write it as a variable. So that's 3.332 divided by S. This is J 0.464, J 26.3, J 1.16, 106, and 0.641. My applied voltage over here is 460 divided by the square root of 3 at an angle of 0. All right, so we'll do in the notes here, we'll do the approach where we have our value of V Thevenin, R Thevenin, and X Thevenin. Those are the calculations. And then we'll just directly plug these in for our max torque and get 229 Newton meters. Again, just doing our Thevenin equivalent approach. I'm not going to go ahead and rewrite the numbers in here. You can see all the details on the board. Our maximum slip, or I shouldn't say our maximum slip, our slip at what maximum torque occurs is 19.8%. And our speed for this 4-pole machine is only 1,444 RPM. So everybody remember what we did in lab, what speed we were getting for our maximum pullout torque? Because around 1270, 1280-ish is what we were getting. So reasonably close, right? And remember, the machines that we had downstairs, that full load speed was 1670 RPM. So that machine was not designed for efficiency. That machine was designed for more robustness, right? Being able to deliver rated power at a lower speed. So it would be reasonable to assume that our pullout speed is going to be, our pullout torque speed is going to be at a lower value. Now, we're going to find our starting torque. And here's the thing. If we want to figure out what torque is for any point, including our starting point, we substitute the value of S that we're trying to solve for that value. When the machine is locked or blocked rotor conditions, your machine is fully slipped, which means slip is equal to 1. So every place in the top equation that I see S, I substitute a 1, and then my equation simplifies down to that. Right? And you end up with 104 Newton meters. Now, if we double the rotor resistance, then theoretically the slip at the maximum torque doubles as well, because my slip is directly proportional to my value of R2. So if I have R2 and I have 19.8, if I put 2 R2 in here, it's reasonable to see that it ends up being 0.396 or 39.6%. My synchronous speed went from 1444 down to 1087. But my maximum torque calculation is still 229. That hasn't changed because, again, the maximum pullout torque is not dependent on that value of R2. My starting torque has changed a little bit. So in the previous case, let's go back up and look. Starting torque was 104. Now it's 170. So it's increased. So remember when we looked at the different NEMA design characteristics, A, B, C, D, when we started moving our pullout torque value back towards 0 speed, because we increased the rotor resistance, we saw how that brought up our starting torque. So again, that's being validated here. Let's take a look at MATLAB. Where is MATLAB? Let's see. Do I have that one up? I do not. So is it this one? Let's see if it's this one. Okay. I think this is the problem, right? If we take a look, let's go back up to my parameters. So 460 volt, 60 hertz, 4-pole, R1, 0.641, 0.332, et cetera, Does that look like this over here? 460, 4-pole machine, 0.641, 0.332, 1.106, 4.464, 46 or 26.3. So those looks like the same parameters. Exactly the same. So now we're going to go ahead and enter our input parameters. These are all our parameters here. And here's our slip calculation to go ahead and get our value of synchronous speed. We did it as omega sub s, and we did it as n sub s. Both of those are applicable. This is the V-Thevenin approach, which I'm just going to show you here. This is the calculation that we do by just, making those assumptions about X1, R1, R2 to simplify, and then we get that value. So what we've done to this point here is we've implemented exactly what we did in the problem. So I'm going to go ahead and I'm going to set a breakpoint to here. And remember, there's nothing up my sleeve. Clear CLC. So I'm going to run. And bring up my results. Where are my results? Here. Oh. So my torque at my maximum, 227.8. Let's go back to here. So using the Thevenin approach, Thevenin equivalency, you get 229. When you do it with MATLAB, you get a little more precision. So the 229 is because of rounding, but you get essentially the same number, 227.8, close enough to 229. Our slip max in our calculation, 19.79, 19.8. Our speed, 1444, 1,443.7 RPM, okay? Now, that is the case of the problem. When I did everything with R2 being that value. Let's go back to MATLAB, and can you see why I put a multiply by 1 over here? Isn't it pretty darn easy to just to say, let's multiply that by 2 if we're going to double the rotor resistance? So I can change that to a 2, whoops. And now I've doubled the rotor resistance. All I've done, nothing else has changed except doubling the rotor resistance. So let's rerun that. Go back and check our results. So we have 0.396 and our operating speed is 1087. Let's go over here. Did I run it? Yes, I did. So the max torque we said doesn't change because it's not dependent on R2, but our slip speed has changed 39.59%, 39.6, and our speed of operation is 1087 RPM, 1087.4 RPM. So we're looking pretty good, hasn't changed. The starting torque has changed, but we didn't do the calculations over here in this MATLAB file, because what I think would be easier to do is to actually define a bunch of points where we're calculating slip, and we're going to start at 0.0001, and we're going to run to 1, and we're going to run 10,000 values of slip between 0.001 and 1. So we should get a really nice curve. And then our slip is going to impact, the only thing it's going to slip in effect is this part right here. Remember that matrix that we did from when we did our loop equations approach? Is that ringing a bell? You can say no. They look like there's some unclear faces, so no problem. Let's bring up whiteboard. And so what we're going to do is change our color. So we have R1, JX1, JXM, JX2, and R2 over S. And this voltage applied here is V phase, which is equal to V line to line, 460, divided by the square root of 3 at an angle of 0. I said 2. Let me clean that up a little bit. Whoops, what happened to my... Whoa. All right, so remember loop equations? We have I stator and I rotor, or I rotor equivalent. And what we said is V phase 0 is equal to R1 plus J X1 plus XM minus JXM minus JXM. And this is R2 over S plus J times X2 plus XM. That gets multiplied by I stator and I rotor. Everybody remember that? By writing loop equations? And then you solve for I stator, I rotor. By taking this matrix, we'll call it Z. because it's an impedance matrix, right? A bunch of impedances in there. We take the inverse of that, and then we multiply it by V phase and 0, and that'll give us our value of stator current and rotor current for any particular value of slip that we want. The only parameter that changes is here, R2 over S. Okay, so we're going to implement that in MATLAB. And since slip is the only parameter that's going to change, voltage doesn't change, none of the other resistances or impedances change, my rotor and stator current is going to be impacted just as I value that various slip. So I'm starting at 0.0001 and ending at 1. But remember the slip equation, slip goes from 0 all the way over to 1. Why did I start it at 0.0001 instead of 0? R2 over S equals what when S is equal to 0? Not a trick question. Infinity, yeah. So if I started this at 0, then I wouldn't be able to get any results, right? I would basically get no rotor current, and MATLAB can't handle that. So what I'll do is I'll just say, you know what? If I do it at a really low value of slip, close to 0, but not actually 0, then I feel pretty comfortable that I'm going to go ahead and do it. And then what I do, and this is the nice thing about MATLAB, is I can set up a matrix, and you'll notice I set this value of n here, which n is going to be an indexing variable. So I'm going to solve for a value of my rotor current, and then I'm going to use that to solve for my mechanical speed of operation, because I'm plotting torque versus speed characteristic. So I need to know what the mechanical speed of operation is. I want to know what my output torque is, but ultimately I really want to, I need to calculate output torque based on what my output power is going to be. And how do I get my output power? Well, it's going to be equal to P converted. If you go back a couple classes, it's 3I squared R times R2 times 1 minus S over S. Why is that that way? Because if you remember from our rotor circuit, this is JX2, this is our R2, and this is R2 times 1 minus S over S, correct? The power that is output over here is the converted power. That's the actual power that is converted from electrical energy to mechanical energy. So once I know what my rotor current is, I can do I squared R, with R being this, and that'll give me my converted power. Okay? So that's why I set up the matrix. And then the last thing I do is I just do a plot. So I plot the speeds. So let me stop this. And remember, up over here, you can see that I've got multiple of 2. Well, let's start with 1. Let's change it to 1, and then we'll go back to 2. Oop. So this is 1. And now I'm going to run it. I'm going to clear all those breakpoints, and I'm going to run it to here or here. One more. I'm going to clear all, and then I'm going to set it. Now, it's a lot of points, 10,000 points. So my curve should look pretty darn smooth. And that is the torque versus speed characteristic for this particular motor. Now, the brute force approach is, if I click a point right about here, it accepts it. That is about the maximum torque that I'm going to get. So remember, it was 229 when it was calculated, or 227.8. When you do it the brute force method without actually doing any assumptions and simplifications, you get almost 231. So it underestimated the actual maximum torque a little bit. And if you recall the speed, when R2 was just its nominal value, I think it's 0.641, You multiply that by 1, we get a pullout speed of 1444. We can see that it's actually a little less than that. 1429 or 1439. Okay. That's our curve. Now, let's go back in and change this to 2. And stop it and rerun it. And we'll wait. It's going to take a little bit of time to bring up the curve. And there's my curve. Did you see the difference between the first one and the second one? Quite different, right? If you didn't see it, one of the things we can do, I think we can do this. Let's try this again. We'll run. That's the original. Then I believe if you type hold, it'll hold that plot. Now, if I change it to 2, it shouldn't, I don't think it should, but it might. It shouldn't rewrite over there. Now you can see it. And that's really the power of doing something, you know, where you're doing multiple calculations over and over and over again, you can come up with a curve really easily. So if you had to plot it yourself, you'd have to do the Thevenin equivalent approach most likely, because how do you enter complex numbers in a software that does plotting? It's pretty much Excel, right? You can actually do complex numbers. It's getting a little bit easier or effective, but it's still trash compared to MATLAB. So you can see how much easier it is. Now, the question is the red line or the blue line R2 equals the 2, its original value, or double its original value? Red or blue? I'm asking the question. You got red or blue? Anybody say red? Anybody say blue? Remember, when we increase the rotor resistance, you're increasing the slip at which torque, max pullout torque, occurs. The pullout torque, it's hard to see, but remember it was 1439 or whatever. Let's take a look over here. Sorry, 230.8, 230.8. It's the same exact value. So we increased the rotor resistance, but we actually haven't changed the pullout torque. We have changed the starting torque, right? We were at, what is that, 107, and we did go up to 2 or 170. And we will change where the operating speed is going to be. But if you have an application where the motor needs to have a lot of starting torque, the only way that you can do that and still have a reasonable machine, like you can always take this curve, instead of a 50 horsepower, 100 horsepower motor, if you put a 1,000 horsepower motor on it, if you have more torque, what's the big deal, right? But that's a very expensive motor and it's not going to be very efficient. But if you take that same 100 horsepower motor and you vary that value of R2, you're going to get the speed and the torque that you want. So we can keep doing that. Let's go back and change this to 3. And we can only increase it within reason. Because at some point, it actually will impact. So slip has gone down, or our slip has increased. We're still getting around 230.8. We go up to 4. Still looking pretty good. Well, that's exactly right. Your starting torque will be exactly what your max pullout torque will be, as long as you pick the value of R2 correctly. So if we continue to increase that, we'll see that here, hopefully. If it's not this one, it'll be the next one, I believe. Oop. So stop and run it. So now here's the green line. Sorry, it's really hard to see. Doesn't want to cooperate. So around 230.8, right? If we go to 0.6 times, I think at this point, we actually will drop our torque. I guess you can't even see. Yeah, so you can see the blue line coming down. You can see that right about here is where that value would be. I don't know if I can select it. 227. So we put too much rotor resistance in here. Now we're starting to affect the output torque. So you can only do it within reason. But ultimately, I'm increasing this. But if I wanted to change the speed control and I didn't have a variable frequency drive, I can put in some more rotor resistance and I can get the speed characteristics I want. You can understand why back in the day they would do this, because they were trying to do speed control. If you're trying to control a conveyor and you want to increase or decrease the speed, you would use this resistance value and increase it or decrease it pretty easily. You can't do that with a synchronous machine because it runs at 3,600 RPM, 1,800 RPM, whatever it is. But the downside of this is, who in their right mind ever puts a resistor in a circuit and expects it to run efficiently? By definition, adding any resistance in a circuit is going to waste energy. It's going to put it out there as heat. So nowadays, you don't adjust R2. You just put a variable frequency drive. Remember we talked about wind turbines being doubly fed induction generators? I said that at the beginning of this material, that you'll put a variable R2 value in there. Well, not exactly. Remember how our speed, and somebody asked the question this yesterday, our speed of the rotor is going to be at mechanical speed. The speed of the stator is going to be at synchronous speed. There's a waveform that causes a magnetic field that rotates faster than the mechanical speed. And what I mean by that is there's an AC frequency that's induced on the rotor circuit, and its frequency is such that that rotating magnetic field plus the actual shaft that it's rotating on, those two add up so that the magnetic field spins at synchronous speed. So your rotor magnetic field and your stator magnetic field both spin at synchronous speed. And it's the rotor field is because you have an AC waveform that is induced on your rotor circuit, and its frequency varies. Remember the FR equation? It was equal to slip times your electrical frequency. So your frequency, I think we did a calculation, it was 1.8 hertz. Well, in wind turbines, instead of inducing it, they just put a three-phase variable frequency drive to put whatever frequency you want on the rotor. So they can either make it additive or subtractive, depending how fast that turbine is spinning, so that you always produce 60 hertz. So the reason why a doubly fed induction generator is perfect, because if I have a wind turbine over here connected to a generator, the output of the generator, I would love to connect that directly to the utility. That's the most efficient. Your generator is a direct connection out. The problem, though, is the utility is at 60 hertz. This had darn well better be at 60 hertz. If it's not, it can't connect because it's going to have a varying frequency, and that will either be a fan or it'll be a wind turbine where it's taking power in. But what ends up happening is, this is the generator part. This is the stator winding. You also have a rotor winding that also has three-phase. And what you do is you run that to an AC to AC converter, and that's how you connect it. So it varies the frequency in a wind turbine, and that's how you can get it. So it always will operate as a generator, regardless if it's going faster or slower than synchronous speed. It's always going to work that way. Whereas if we only increase the rotor resistance, our wind turbine always has to spin faster than synchronous speed to produce electricity. But with this design, it can spin as long as the speed is fast enough to overcome the losses. That's called cut-in speed. It should be producing power. It's going to be effectively doing that. It changes. So remember, the synchronous speed is always 60 hertz. It's just that on the rotor, this rotor is spinning, let's say it's spinning at 40 RPM. And remember, this stator here, it goes through a gearbox, so it gets it close to either 1,800 or 3,600 RPM. So what happens is, this here is spinning at 40 RPM. This is spinning at, let's say, 3 RPM. So the concept of we're a bug on a shaft, and we look like, if we're standing here stationary, we look down at the bug looks like it's not moving, or if it starts to walking, it looks like it walks a little bit faster. But relative to that stationary item, that bug is going whatever the shaft speed is plus, whatever it's walking in. So it's just changing your frame of reference. How many here say the sun rises in the east and sets in the west? Be honest. Oh, only a few honest people. Is that true? Does the sun rise in the east and set in the west? What happens actually? The earth rotates. But we change our frame of reference, right? Because we are rotating with the earth. So we don't actually see what a stationary, if you were standing on the sun, you would see that rotation. It's the same idea. When your car is going 50 miles an hour or 65 miles an hour in the direction of east to west or west to east, and you were standing stationary, you might look like you're either going faster than the Earth's spin or slower. It's the same concept here. Okay. Really important, because this is also how we used to do things with rotary converters, how we could get a variable frequency device without using power electronics. Used to happen all the time.
Question, Paul, about shorting windings on an induction motor. Does it have the same? I know with permanent magnets that we use here, if you want to keep it locked like a wind turbine or whatever, if you short the windings on a permanent magnet motor, it's got a huge torque.
Well, on a permanent magnet, you're talking about the rotor or the stator windings?
Sorry, the stator windings.
Okay. So you'd short them, and if you do that, what ends up happening is you just have two magnetic fields and they would be locked in, correct? Yeah.
So I'm assuming on an induction motor, even a doubly fed one, if you shorted all the windings together, it's still going to let it spin.
Yes, it would, but the stator windings wouldn't last very long because they're not designed to handle that amount of current. Just like on your permanent magnet motor, right? If you actually shorted the stator windings, you would have more current than what it's designed for, and you potentially would burn it up. You can short our mortar or field windings and not have any issues because you just have magnetic fields there.
They're used commonly for like just parking brakes.
Yep.
For these systems. So I was just wondering if for induction motors, since there's no magnetic field, even though you've shorted everything, there's still no permanent magnet. If you don't have any current running through it.
Right. Once you have no current running through, you have no rotating magnetic fields. So it's just a hunk of iron rotating in a field.
Right. Okay. Thanks.
There's nothing there. And that's one of the biggest problem with wind turbines. If I have a fault out here on the wind turbine bus where that connects, what happens?
It goes to freewheel.
The voltage goes in the crapper, right? And we no longer have a current here that can get that magnetic field on the rotor. So the voltage field collapses very quickly, which means my magnetic field goes away, and I just have a hunk of spinning metal. I can't produce any current. So these wind turbine, these doubly fed induction generators are terrible for supporting the grid under fault conditions because they exacerbate the fault. When a fault occurs, all the voltages on the system are changing and are dropping. You're feeding a lot of current to one location, so the system voltage starts to collapse. Well, now you have wind turbines that basically shut off because they have no magnetic field. So they exacerbate the fault. Now the voltage that was, at 1 per unit or 100% went down to 90% because of the fault. Now it's gone down another, let's say 3%, because your wind turbine generators are also not contributing. So wind turbine generators have had a real problem. And you can look at the terminology, and Nate, I don't know if this applies to you, but a lot of renewable energy equipment have requirements called low voltage ride through capability. So if the voltage goes poor, you have to be able to ride through, or I can't remember the time, a certain period of time, and you can maintain the voltage so that the fault can be cleared and you can keep the wind turbine generation online. Because if a fault goes, that means equipment is damaged. You've lost something in your system, which means your system is degraded. Now you've lost a bunch of generation, which degrades your system even further. And before you know it, your system is completely turned off and shut down. So that's called low voltage ride through capability, kind of an important thing. If you go up over at Passadumkeag, just up the road, they essentially have superconducting. I don't know what they're called. They're not synchronous condensers. They're superconducting static bar. I think they're static bar compensators. They have 3 of them there, and their whole purpose is just to maintain the grid in the event of a low voltage. The wind turbines can't help you. Permanent magnets don't have the same issue because they always have a field. The problem with a permanent magnet, so you could ever do things with a permanent magnet, but here is the biggest problem with a permanent magnet one. Your entire output has to go through your semiconductor device. Over here, maybe 5 or 10% would go through that, and the rest is hardwired. Over here, you have 100%. What does that mean? Big, expensive, 100% rated pieces of equipment to handle the amount of current that goes through your system. So this is a far cheaper option and more efficient. And has been for a long time the predominant wind turbine generator type for many, many years.
Some are looking at magnetic gearboxes, so it's a permanent magnet motor inside a permanent magnet motor kind of thing.
But the generator itself is still going to be a doubly fed induction generator, right? Or
No, it's
you're just going to change the speed through that?
No, it would be like your lower picture there, but the
Yep.
generator has, because you have the very, very low output RPM, and you want to get high frequencies for control, you have a permanent magnet rotor, and then there's somehow another permanent magnet rotor around that one,
Okay.
and then a stator winding, and it creates an artificially larger number of poles. It's a very weird technology, but it's how you can use. It's a compromise, so you don't have to have a gearbox, a mechanical gearbox that you have to keep refilling oil on.
Yeah, that all wind turbines have gearboxes, because to get a generator that can handle the torque that has 50 poles, it would be the size of this room.
Oh, they're
Okay.
huge.
Yeah, you can't have that at the top of a tower that's 250, 300 feet in the air. It's just not practical. So what do? You put a gearbox up there, even though it's not efficient and you got to do maintenance on it. The gearbox makes things so much smaller, makes it practical. So yeah, that's the regular, unfortunately, that's the regular maintenance thing on an electrical wind turbine, is you got to change the oil out on the gearbox pretty regularly. All right, questions on that? But that's how wind turbines used to do. They actually had it. If you look, I think it's Vestas had something called OptiSlip, was one of their turbine designs. I don't think they still make it, but it essentially was putting in a very evaluative R2. They called it OptiSlip. Where do you think the slip comes from? It's the slip equation that we talk about here. And Opti, I guess, optimum slip. So that's where they would come up with that. Any questions on this MATLAB file? Because the last little thing I did was I just did calculations based on 1, 2, 3, whatever, for slip. So we can go back to MATLAB and release the plot. And then we'll change this back to 1. And run it. And we're going to run the whole thing. And then we'll look for our value of torque. And this just basically what location, you don't have to actually keep this, but that actually tells me the location in the matrix. So that doesn't tell me anything. But we said 229 was the maximum or pullout torque, 230.8. So this is more accurate. And the speed was 1444 using the Thevenin equivalent approach. We have 1437's actual. I think we said 19.8 versus 20.14 for a slip of 1 times R2. We double it, we run it again. And let's see, torque is still the same, 430.8. Our speed, I don't remember what our speed was for doubling, but it was 1,000 something, I remember that. So we're at 1,075, and our slip was 39.6%. Now it's 40.3%. So the brute force method, which just means you have to do 10,000 calculations, gets you the exact results, but doing the Thevenin equivalent approach is pretty darn accurate, right? Not that far off. So it works really well. Okay, questions on, where am I? This material. Because we're ready to move on to some testing. Any questions? Okay, let's move on to, I think we're on to this one here. Come on. All right, so let's determine some motor parameters. And remember, the induction motor is just like a transformer, but it's short circuited and it gets to rotate. So we're going to do very similar tests to the transformer, but the rotation has to be a slightly different approach. So the transformer test, we did the open and the short circuit test. What would be the equivalent of open and short circuit tests for a motor that rotates? Open circuit was another way to say the no load test. How do you have no load on a machine? You just run it without anything coupled to it. So my slip is almost equal to 1, right? I mean, 0. So the no load test is the test when slip is almost equal to 0. How about the short circuit or load loss test? The analogy here is we want as much load as possible on this thing. How do you get as much load on an induction machine? You take a chain, wrap it around the shaft, tie it into place, and don't let it move. It's called the locked or blocked rotor test. So we performed the no load or open circuit, if you want to call it, or shaft is allowed to freely spin with as little load as possible. And then we do the full load or block rotor test. Unfortunately, that's not the whole spiel that we need. We also need to do the DC test because we can't tease out some of these resistances without knowing one value. So the only additional test that we need to do is the DC test. So here's our test. Here's our DC test. This shows a Y-connected machine. Now, what happened to my equivalent circuit that is over here? Here's the actual per phase equivalent circuit. We've got 1, 2, 3, 4, 5 impedances. What happened over here? Now I'm down to a single impedance. Remember, this value right here is the R1 that's in the circuit. What happened to the rest of those impedances? What happened to the other 5? What happens to an inductor when you apply DC?
Those become short effectively.
Short circuit and short circuit. I don't even care about the R2 because I'm short circuiting. So the only thing that I have left is R1. And because this is a real world machine, I don't necessarily have access to all 3 poles of the windings. I just have access to the 3 leads. So I'm going to run my DC test. This shows a Y-connected machine. So in my Y-connected machine, I have 2 resistors, which are in series with each other. Okay. So the DC test means run DC to any 2 leads, measure the current and the voltage, and you want to drive the DC so that you're getting rated stator current to get as accurate a measurement as possible. And that's the value that you get. You can see that my voltage divided by my current is my DC value. I have 2 resistors in series, so my R1 is going to be equal to my DC value divided by 2. How about for this circuit here? If it's delta connected, I run a DC test. What do I end up with?
A resistor in parallel with resistors in series.
R1 in parallel with 2R1, right? Product over sum. So that's my DC value. If I want to solve for my R1, I just invert and go over there. That's how I get my DC value. I mean, my R1. So
On
you
an a-
would, what's that?
On an actual like FAT, would they do that on like all windings to make sure that they're all the same?
Yes, very good question. So anybody know what an FAT is? Other than something that's delicious that you eat? Bad joke, sorry. Factory acceptance test. When you buy a motor, if it's a decent sized motor, if it's an off the shelf, well, I shouldn't say off the shelf. If it's 50, 100 horsepower, those are fairly common. You can order them from Baldor or Reliance and you can get them a dime a dozen. So they might not have a factory acceptance test result, but if you're buying a motor, a custom application where it's a big motor or it has some different characteristics, you might actually put it through its paces to get some real test data. To be frank with you, I've never, other than working at a nuclear power plant, I've never seen any factory acceptance testing of motors. They do a mega or a high pot just to make sure you don't have any bad insulation, and then they plug it in. I don't know if that's your experience, Nate, but
No,
usually
mine are weird.
you
so-
get different experiences.
Yeah, but mine are very specialized. So,
Okay,
but we've had full FATs.
okay. Yeah, literally, I mean, you could go to Reliance and order a 50 horsepower motor, and unless the supply chain issues are still a problem, you could get one in a couple days. 50, 100, maybe 200 horsepower, maybe 250. Once you start pushing 250, your voltages start to change, and those aren't something you can just find locally. Those get to be a little more custom, where you would actually maybe would have to have more detail. And the factory acceptance test might be define what you want for resistances and efficiencies, and you actually would test all three lead combinations to figure out an average R1 resistance. So if you wanted higher levels of precision, you would check all the values of R1. Okay, and then you just take the average, essentially, just like we did for the transformer. It's the same thing with the transformer. If you're buying less than a 5 MVA transformer, those are kind of standard off-the-shelf items. So you just get what you get. And so they would be, they would give you some typical data. Mainly, they might not give you a full-blown factory acceptance test, because a factory acceptance test costs a lot of money. It's not cheap. Okay, so if you don't need to do one, don't do one. All right, does this look familiar at all, this test setup? This is what we did in lab, right? This is the 2 watt meter method, where all you need are 2 voltages and 2 currents, and you can calculate power. You just have to set the things up correctly. So, no load test, you have to energize all 3 phases. You can't take an induction machine and just energize 2 phases. All 3 phases have to be energized. You decouple the motor from whatever it's connected to. And sometimes there's a keyway that has the coupling. Sometimes there's an actual mechanical coupling that's bolted together. You completely remove that, and all you have is whatever the shaft is spinning at. That's going to be the lightest load that you can apply. I would imagine some people are crazy. If they want to reduce the friction and windage losses, you can, try to sand down the shaft, polish it a little bit. You also can put it in a chamber where it doesn't have air. You could use hydrogen, because hydrogen, where's hydrogen on the periodic table? Number 1. Why is it number 1? One little electron available, right? And its density is really small, so it's light. It's very light gas, right? So if you have really high power applications, nuclear power plants use hydrogen around their rotor circuits, around their rotor. And the reason why they use hydrogen is because it's such a light gas, you can reduce the friction and windage losses. And I guess it's worthwhile enough for them to do hydrogen, even though hydrogen is explosive and all this stuff. They still want to use hydrogen to provide the cooling around that, and it just reduces that. So you could do that, but I don't know if they actually do it, because like I said, I've never seen any factory acceptance testing for motors. So your motor is allowed to spin as freely as possible. Hopefully your bearings are new and all lubed up and ready to go. You only have small friction and windage losses. So your converted power is whatever your friction and windage losses are. Your slip is almost zero. Here's my circuit. So I've got the full-blown circuit represented here. Pencil, here it is. So here is my circuit. My slip value here, 1 minus a really small number, 0, fairly close to 0. What ends up happening is that term is very, very small compared to R2, because I'm essentially dividing by 0. And this value here is so much greater than X2 that my final circuit looks like this. Okay, I have my core losses, my magnetizing losses. I still have R1 and X1, but everything in the rotor circuit has been replaced by a resistor that is equivalent to the friction and windage losses. So now I've got, if I can throw away my core, or I can combine that into my friction windage losses, then I end up with this value. This value here is going to be much, much greater than X of M, or should be much, much greater than X of M. So, whoops. What I see is that this value here is so much greater that most of my current is going to flow through there. So now I continue going. My rotor copper loss, I2, is going to be negligible because my R2 is my R2 times 1 minus S over S is so large. My input power is just going to be equal to 3I squared I1 times R1 plus whatever rotational losses. My equivalent input impedance is approximately equal to X1 plus XM. So what I have is my magnitude of my input here under my no load conditions is essentially going to be equal to this and that, X1 plus XM, because XM is going to be so much larger than R1, and X1 is going to be large enough that I can neglect that value. So I can solve for X1 and XM. How do I do that? I have to figure out a way to find another term to introduce to figure out. So all I've done under my no load condition is solve for these two, but I have one equation and two unknowns. So I have to introduce another equation and maybe get there from here. So let's do the block rotor condition or the lock rotor test. At this point, my slip is going to be equal to 0. So this term becomes R2. These terms are going to be so much greater than the combination of those two that I can throw them in the trash. All right. So my rotor resistance is going to be R1 plus R2. That's the real part. And my lock rotor reactance is going to be X1 plus X2. That's all I'm left with. These two and those two. The R sub C and the JXM are out of there. I don't have any converted power because it's not rotating. It's locked in position, right? So there's no converted power because power equals torque times omega. Omega is in fact 0. So there's no converted power, just like there's no friction and windage losses. Those are all 0 because it's not allowed to rotate. Okay? Yes, sir. Oh, yes. I said 0. I should have said 1. Thank you. Slip should be 1. 0 when it's essentially at no load. So this is my input power. Don't worry about it. I have my values. And here is my value for X1, X2, R1, and R2. Now, here's one thing to keep in mind. When I'm running a machine where the shaft is locked, you remember when we were in lab, or for those of you who did it in TV land, when we were in lab and we ran it as high a load, what happened to machines? What happened to those induction motors in lab? They didn't spin very well, did they? They sounded like they were dying, making a lot of noise, and they didn't sound healthy, which is exactly right. Putting those machines in those conditions is not particularly healthy for them. So you can't run those for long. But one of the things you can do is you run your frequency at a lower than rated frequency. Because remember, if my stator field is running along at 3,600 RPM or 1,800 RPM, whatever the number of poles are, that's spinning along really fast. The dpdt is quite high. If I drop my frequency, dpdt is going to drop as well. So if I can, I'm actually going to perform the test, not at 60 hertz, but maybe 30 hertz, maybe 20 hertz, maybe 10 hertz, whatever value it is to reduce it. So I don't have to work as hard. So if I run that at a lower frequency, I only need to go ahead and correct the X value, because omega times L is equal to X, and omega is 2 times pi times F. So if my test frequency is different, I have to correct those reactances based on that test frequency. Now I had that third equation, or my second equation, and I know what R1 is. R2 I should be able to tease out, because when I take V divided by I get Z, which is equal to R plus JX. R is going to be equal to R1 plus R2, and X is going to be equal to X1 plus X2, right? So I only added one equation by breaking up the terms in the real parts and the imaginary parts. I actually have two separate equations. One equation has R1 plus R2. I got this value from the DC test. Now I can solve for R2. I have this equation, one equation, but two unknowns. And then in the previous case, I had one equation and two unknowns. So I don't have enough. So I have two equations, but three unknowns. I have X1, X2, and XM that are unknown. But the two equations I have are V no load divided by I no load is equal to this here. And V blocked rotor divided by I blocked rotor is equal to X1 plus X2. So I have those two, but I have three unknowns. So the only thing I need to do is I have to use some design parameters, some additional information to go ahead and get the result I need. So this is a table that will help you define what are my values for X1 and X2. And it's NEMA design specific. So depending on the NEMA design characteristic, if I have a locked rotor value, so remember so I have Z locked rotor is R locked rotor plus JX locked rotor. My X locked rotor is going to be equal to X1 plus X2. This introduces that additional equation. This one says X1 is equal to 0.5 X lock rotor. X2 is equal to 0.5, or they could be 0.4 and 0.6, 0.3, 0.7. We don't know. But having this table is a way of introducing another equation. Because once I know what X lock rotor is, I can solve for X1, or I can solve for X2. And that's how your real world tests are going to determine parameters. These are the tests that you would perform if you're doing factory acceptance testing and actually getting test data. Because remember, the designers figure out, okay, how many turns of windings, what metal I use, what is the pitch that I need, how do I have the spacers, what type of magnetic material I use, et cetera, et cetera, et cetera. That's all well and good. But when I actually energize the motor, I want to know that its characteristics are what I expect. So I still will put it through its paces, unless I know, I've got it designed so well and it's these parameters, it never changes, then I wouldn't have to do the testing. But this is the test. Like I said, I've never actually seen a factory acceptance test. That's why for a motor. That's why I can't share any data sheets because I don't actually ever have them. I don't know, maybe Edge, we can find some on Edge. But so let's see. Three-phase induction motor. Factory acceptance test. I can't imagine this stuff is going to be all that available, but well, here we go. Maybe we can see this is a medium voltage motor. So this would typically be anything over 1,000 volts. So this is 20,000 horsepower or 20,000 horsepower, 4-pole machine. So here are the tests: no load current, no load power. Oh, here we go. So it says no load current, no load power. This one does locked rotor current by calculation, no load speed. There's also a bunch of different tests here. There is this locked rotor current test as well. Full load current and slip, power determined. So this does look like you would have some of that stuff that you could find. And so here, IEEE standard 112-2004 would be the way to get the information about how to do that. But like I said, I've never personally seen test data, so I don't know. But no load and full load current, yeah, it doesn't seem to have that information. Okay. We'll pick this example up in the next class. And we'll do it all by hand. We'll do it on whiteboard. And we'll do that. And then we'll do NEMA KVA code, which is starting code. And then that'll be pretty much it for induction motor. So questions? TV land questions? Okay, well, if there are no questions, have a great day. I'll see you all on Thursday. Take care, everyone.